Yes. No, that's okay. I just want to say that the afternoon session, yes? Yes. This is the mic, right? It's okay. Anyway, I'll put this here. Yeah. How many people are online? Shall we start now? Yeah, all right. So welcome to the last second session. And Professor Kühnel from Stuttgart will speak about generalized Heawood numbers. And actually, he will not speak. Well, on behalf of him, Biplab and Nitin will do the talking.
So, hello everyone. Welcome to the afternoon session. I am Nitin. I did my PhD under Basudeb Datta. So I'm not surprised to be here. I was actually planning to be here. I am surprised that I'm actually talking and presenting something. So yeah, so Professor Kuhnel has prepared these slides, and unfortunately he cannot make it here. So Biplab and myself will be presenting these slides here. So this is on generalized Heawood numbers. So let's get into it. So to motivate the problem, so we have this sort of a famous, easy to understand problem. How many colors do you need for coloring a given map of countries in a plane or in any other surface such that adjacent countries are colored with distinct colors, right? So in a plane or a sphere, that is the typical map coloring problem. And you can also ask this question the other way. You essentially put a point on each country, and when two countries share a border, you draw an edge. So then coloring this map of countries essentially reduces to coloring this graph so that any two vertices which have an edge has a different color. Right, so how many colors do we need to be able to color any such map on a plane? So this is what exactly that says, that each country leads to a vertex on the graph and two vertices are adjacent if and only if corresponding countries are adjacent. So obviously we know that we can embed a complete graph on four vertices into the plane or sphere, which means at the minimum we are going to require four colors to be able to color any map, right? So as a consequence is the famous four-color problem for the plane or the two spheres. Of course, this gives the lower bound on the number of colors that you're going to require. You can indeed do it with only four colors, as we know, any map, and that's due to a lot of IBM computers. Yeah. So similarly, you can there's a map of you can draw a map of 7 countries on a torus such that the dual graph will turn out to be a complete graph on 7 vertices, and so you need at least seven colors to color a map on a torus. So as you sort of increase the genus of the surface, you can embed bigger and bigger complete graphs there, right? So this is the initial setting. So okay, so what it says is if there's an n vertex. So what is the minimum number of vertices you need to triangulate a surface? So that is characterized. So the lower bound is given in terms of Euler characteristic of the surface, which is this, and so this equality holds if any two vertices in the triangulation have an edge, right? It's called two neighborly. And similarly, the for surfaces, two-dimensional surfaces, you have how big of a complete graph can you embed, and that again. So the upper bound on the size of the complete graph is given in, again in terms of Euler characteristic, and you can see that these are actually the same. We have a proof of these in the slides, and it's not difficult. So this is the proof of the first. Yeah, I think the first one is the proof of the first. Yeah. So if there is a n-vertex triangulation, you will have this inequality, and that is just by you write Euler characteristic in terms of vertices, edges, and triangles, and you note that every when you count all the triangles, you essentially count each edge twice. We do this algebra here, and we get the proof apart. Similarly, you can prove the other way, like if you can embed a complete graph of n vertices in the surface, we can again compute its Euler characteristic, and this time we can bound the Euler characteristic from above, and it turns. We can see this. Essentially, it's Euler characteristic of the graph and the complement of the graph, and so for each face, we have n minus n choose 2 plus f for each of the faces in the complement, right? So yeah, so if we solve this equation, we essentially get this gives in terms of Euler characteristic, but we can also, if it's simply connected, we can sort of write it in terms of first homology. So this is essentially any minimum triangulation. Essentially, this is the lower bound it has to meet. So, in fact, most surfaces for all most of the topological types, we actually have triangulation matching this lower bound. So, with 19 vertices, we can construct triangulate an orientable surface of genus 20. And yeah, as all other cases except for Klein bottle can be realized meeting this lower bound. So similarly, there's we can go to 4 dimensions, and so now we are looking at generalization. So now we so any n vertex triangulation of a 4 manifold is suppose this is the equivalent of the inequality for the case of 2 manifolds. And this happens only when all possible triangles are present. Yes, so again, I've not verified these simplifications, but essentially you again get a lower bound on the number of vertices needed to triangulate the manifold. In terms of its, this time it's in terms of the second Betti number, because the first one, I guess, vanishes because it's simply connected. It's 3 neighborly. So this is in, yeah, so beta 1 for 2 dimensions is replaced by beta 2 for 4 dimensions. And the conjecture actually is sort of a generalization of this to a general 2K manifold. And so simplicial complex with n vertices is called K neighborly if it has all the K minus 1 dimensional simplices. So yeah, so there's for reaching a certain Euler characteristic, one, yeah, more and more edges triangles we have to add. And yeah, so if you want to embed a bigger and bigger complete graph, you so yeah, sorry, I'm a bit confused here. Let somebody else explain it. Yeah, so essentially this is the generalized inequality for a general 2K manifold. That so this is again in terms of Euler characteristic. There is a more refined set of inequalities when we do not assume that the manifold is highly connected, and then we have inequalities for each Betty number in some sense from beta 1 to beta d by 2. So maybe now I'll ask Biplab to take you over the rest of the conjecture. Yeah, yeah.
Yeah, so good afternoon, everyone. So I am Biplab Basak. So currently I am a faculty at IIT Delhi. So I have completed my PhD under the guidance of Professor Basudeb Datta in 2015. So currently I feel actually very lucky that I am presenting the slides prepared by Kuhnel. I have not met him, but I heard a lot about him. So anyway, so we can start. So one more thing actually. So since I have around 20 minutes and to complete around 20 slides, so I will go little bit faster. So if you want to read the slides, then please do not hesitate to stop me. Okay, so here is the generalized Heawood inequality. So it was conjectured by Kuhnel in 1993 and proved by Novick and Schwartz in 2009. It says that so let M be a closed 2K manifold triangulated with n vertices. Then the generalized Heawood inequality this one holds. And the equality holds if and only if the triangulation is K plus 1 neighborly. So that's mean the triangulation uh, do not have any missing K simplices. And this will imply that M is K minus 1 connected. That's mean that the ith homotopy group is 0 when I is up to K minus 1. Okay, so here is one example. So any triangulation of SK product SK requires at least 3K plus 4 vertices. And right. So because the Euler characteristic chi for SK product SK is 4 when K is even and 0 when K is odd. So therefore this value is 2, and therefore we can calculate that n bigger equal to that number 3K plus 4 vertices. So yeah, so consequently, so we can define a generalized Heawood number for M as the n realizing the equality in 5. But obviously it is an algebraic number, but in general the explicit algebraic expression is impossible. But for k equal to 3, the polynomial is biquadratic. Therefore, for a 2 connected 6 manifold with the third Betti number beta 3, the generalized Heawood conjecture becomes this one. And if M is not highly connected, then one has to find other inequalities, especially adapted to the topology of M. It is because Arnoux and Martin, they proved that for a triangulation of CPK, one needs at least K plus 1 whole square number of vertices. But here Euler characteristic is K plus 1. So, right. So therefore, uh, if you put just the value of this one, then you will get the in inequality 5, then you will get a weaker inequality. And obviously, you can see that this is very trivial for odd K. Oh, okay. Okay. So yeah. So for D manifolds with Betti number beta j, where j is varies from 1 to d by 2. So right. So if the manifolds are not highly connected, then we have similar inequalities, at least as conjectures. Next. Next. Maybe I do that. Then it will be Okay. Yeah, better to keep the whole slide so that, yeah. Okay. So for d equal to 2, yeah, so we have this inequality and it is due to Heawood. And for d equal to 3, we have this inequality and it is due to Lutz, Solanke and Schwartz in 2009. And for d equal to 4, we have this inequality again due to them. And for n equal to 11, we have one examples of for equality and it is given by Wakap in 1970. And for n equal to 15, 26, 21, 26, 41, we have some examples of for equality, and it is given by Professor Bakchi, Professor Datta, and our Nitin.
So somehow that mouse has taken over.
Yeah, it is fine.
Oh, okay. Fine.
Okay, it is fine. It is fine. Yeah, but just keep the full slide, then it will be fine.
Okay.
No, 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 no. Yeah. Okay. Right. Now for d equal to 4, if beta 1 equal to 0, then we have this equal inequality. And again, for n equal to 6, we have the natural examples for equality. That's when we have S4, which is the boundary of 5 simplex. Then we have the equality. And for n equal to 9, Kuhnel gives one triangulation, that 9 vertex triangulation of CP2, which is again realize the equality. And for n equal to 16, Kasila and Kuhnel in 2001 again gives a triangle 16 vertex triangulation of K3 surface. Again, it realized the equality. Okay. Yeah. Now, these inequalities can be presented by a Pascal-like triangles depending on D and J as follows. So you can see that for D equal to 2 and 3, we have this single inequality. For d equal to 4 and 5, we have these two inequalities. For d equal to 6 and 7, we have these three inequalities. And for d equal to 8 and say 9, we have these following uh, four inequalities. That's when you can see that these inequalities follow some kind of Pascal-like triangle. And next. Yeah. So here is the main conjecture. Actually, recently in 2018, so there is one paper by um, Karim, yeah, Arif Sajid. So he actually give one proof of this. He claimed that so this conjecture is solved, but this work has not been published yet. But so for the timing, we can assume that it is a conjecture, and here it is. So let M be a closed connected D manifold, and let J be an integer between 1 to D by 2, and beta J denote the corresponding beta number of M with coefficients in a field. So as standard case, we can take Z2. So then for any n vertex triangulation of M, the number n satisfies these two inequalities. Next, I think something is there. Yeah. So now here one can check that if D equal to 2k and if M is k minus 1 connected, then beta k equal to this number. And therefore this inequality 8 coincides with the inequality 5. Sorry. This? Oh. Oh, it is working. Oh, fine. Okay. Yeah, fine. Now the case of equality can be conjectured as follows. So that was our this one we can for a time being we assume that this is our first conjecture in this slide, and this is the second conjecture. So here the case of equality we are talking about. Yeah. So equality in the above inequality implies that the triangulation is J plus 1 neighborly. So J plus 1 neighborly will automatically imply that beta 1, beta 2 up to beta J minus 1 equal to 0. And again, by using the duality, one can check that beta D minus J plus K to beta D minus 1 all are 0. And also this inequality, the equality of the above inequality also implies the second one. That is beta J plus 1 beta j plus 2 up to beta d minus j minus 1 all are 0. So in short, one can say that beta j and beta d minus j are the only non-vanishing Z2 numbers other than beta 0 and beta d. And therefore, for j between 1 to d by 2, M has the same Z2 homology as connected copies of Sj product is d minus j. Okay. So here are the special cases where the conjecture are already proved. So for d equal to 2, we have Heawood inequality, which is given in 1. For d equal to 3, yeah, both conjectures are true due to, again, Lud, Solanke, and Schwartz in 2009. For any d and for j equal to 1, the first conjecture is true again due to them. So for k minus 1 connected to k manifolds, so this is generalized Heawood inequality above. Again, it was proved by Novik and Schwartz in 2009. For j minus 1 connected manifolds with beta j equal to 1, and for any arbitrary d bigger equal to 3, the first conjecture follows from an priori bound due to Brahim and Kuhnel in 1987. And moreover, for j equal to 1 and beta 1 equal to 1, and for arbitrary d greater equal to 4, the second conjecture follows from the uniqueness of the sphere product of S1 product SD minus 1 with the minimum number of vertices 2D plus 3. And also, this is work done by Bakchi in 2008 and the others as well. Yeah, that ith homotopy group is 0 up to k minus 1. No, the high it is homotopy. It is homotopy group, right? So yeah. Okay, so now we are moving to the reverse direction, and it is kind of Van Compen-Flores problem. So yeah, it is easy to see that the complete graph K5 cannot be embedded into the two plane or two sphere. And another formulation of that is, so the n skeleton of an n minus 1 dimensional simplex can be embedded into the two sphere if and only if n is less or equal to 4. And a direct generalization to the higher dimension is known as Van Compen-Flores theorem. Actually, this theorem was proved by Van Compen and Flores independently during 1932 and 33. So the K skeleton of an n-1 dimensional simplex can be embedded into the two sphere if and only if, 2k sphere if and only if n is less or equal to 2k plus 2. Right. So as a common generalization of this theorem and the Heawood inequality, so Kuhnel has proposed this one in 1993. It says that it is also a conjecture, and this conjecture says that, so if the K skeleton of an n-1 dimensional simplex can be embedded into a k-1 connected 2k manifold, then the reversed generalized Heawood inequality, this one holds. Okay. So now we will discuss some regular cases in both Heawood inequalities. So any k-1 neighborly invertex triangulation of a 2k manifolds M contains an embedding of the complete k skeleton of the n-1 dimensional simplex into M. But the convert is still open. It says that can any embedding of the complete k skeleton of the n-1 simplex into a 2k manifold M be extended an invertex triangulation, provided that the equality in the generalized Heawood inequality holds? Yeah, so he says that possibly that counter examples can be constructed by cone Schober knots as a part of the embedding. Yeah. Now here are some examples of regular cases. So the known n-vertex triangulation of 2k manifolds where n equals the generalized Heawood number. So for k equal to 2, that is for 4 dimension. Again, Kuhnel proved that. So to give one example of 9-vertex triangulation of CP2, which is unique, and also our Professor Basudeb Datta and Bakchi, they have also some works on this one. Yeah. So right. So also in 4 dimension, Kasela and Kuhnel gives a 16-vertex triangulation of K3 surface, which realize the equality. Yeah. So for k equal to 3, that is in 6 dimension, Lutz gives an example of 13-vertex triangulation of S3 product S3. And for k equal to 4, that is in 8 dimension, Brehm and Kuhnel gives an 15-vertex triangulation of that HP2, this one. So yeah, so currently in the last week only, so we have another result in archive, so given by Gaffulin. So he gave for k equal to 8, I think, right? K equal to 8, that is the 27 vertex triangulation of Cayley projective plane. So it is very interesting in the also in the sense that when Kuhnel prepared these slides, then that problem was not known, and now when we are talking about that one, and then it is solved. Okay, that is like okay, that looks like one, right? Yeah, yeah. Okay. Okay, so here are some approaches. So recently new approaches were made for proving at least some weaker versions of this Van Kampen Flores type conjecture by cohomological methods. So one can define a so-called Van Kampen abstraction to immutability in terms of a certain cohomology class. So the vanishing of the abstraction is then shown to be necessary condition for immutability. And these results imply those conjectured above are true in case of beta k equal to 1 and if the intersection form is Q symmetric with beta k equal to 2. And here is a corollary of that one due to them. So the conjecture above is true for k equal to 1 due to Heawood, and for the projective planes over C, H and the Cayley number, and their looks alike. And moreover, it is true for all sphere product SK with odd k and all SK bundle over SK with the intersection from 0, -1, 1, 0. Right. So here are some problems he stated concerning the conjecture of that Van Kampen Flores type. So can the 2 skeleton of the 8 simplex or of the 9 simplex be embedded into S2 product S2 or into a connected sum of 2 copies of CP2? And due to Kuhnel and Lashman, it is known that there is no 10 vertex triangulation with a complete 2 skeleton. Now there is another problem. It stated that can the 4 skeleton of the 15 dimensional simplex be embedded into S4 product S4 or into any other S4 bundle over S4? And there is another similar problem is that, so can the 4 skeleton of the 15 dimensional simplex be embedded into the connected sum of 2 copies of SP2? Right. So here are some more problems. So this is one problem that find more n-vertex triangulations of 2k manifolds satisfying the Heawood equality in 5. That is when n equals the generalized Heawood number. And these are the natural candidate. You can just read that one. So for 14 vertex triangulation of 6 copies of connected sum of S2 product S2 and 16 vertex triangulation of 11 copies of S2 product S2 and so on. And that also that 20 vertex triangulation of Cayley projective plane. So we have that article I was just talking about. Yeah, so here are some more problems. So again, you find more n-vertex triangulations of 2k manifold satisfying the equality in the other conjectures inequality, that is that Pascal-like triangles above. So this one known examples due to Lutz for d greater equal to 5, it is 12 vertex triangulation of S2 product S3. And these are the natural candidates, so it is not proved, so one can try to prove this one. So these are the 21 vertex triangulation of 5 copies of S1 product S4, 20 vertex triangulation of 13 copies of S2 product S3, and so on. Right, so here are two consequences for the sphere product. So any triangulation of SK product SK has at least n plus 3k vertices, and n equal to 4 plus 3k if and only the triangulation is k plus 1 neighborly. So again, there is another consequence of that two conjectures. If they are true, it is so any triangulation of SP product SQ with P less than Q has at least n plus P plus 2k vertices, and equality implies that the triangulation is P plus 1 neighborly. Yeah, so probably we will finish within time. So we have the similar kind of results for the centrally symmetric triangulation as well. So yeah, you can see that a triangulated manifold is regarded as centrally symmetric if it admits an involution without fixed point. And in this case, the K skeleton of the simplex is replaced by that of the cross polytope. And by the work of Jungermann and Ringel, there is an analogous centrally symmetric Heawood number in two-dimensional case, and it is this one with unique 8-vertex centrally symmetric torus as an example of equality. And in higher dimension, centrally symmetric versions of both Heawood inequality were studied by Sparla in 1999, maybe from 1999. And in case of a 4-dimensional simply connected manifold, we have this inequality. And by putting n by 6 equal to m, yeah. So we have this one, and by solving one get n bigger equal to this number. Now again for n equal to 12 and beta 2 equal to 2, the equality is realized by Sparla's highly symmetric triangulation of S2 product S2. And for n equal to 16 and beta 2 equal to 14, there is an example uh, of right that 16 vertex triangulation of maybe space which is homeomorphic to 7 copies of S2 product S2. It is given by Effenberg and Kuhnel in 2010. And for a two connected 6 manifold, we have the Heawood number in the inequality this one, and equality in case of beta 3 equal to 2 is realized by a 16 vertex triangulation of S3 product S3 given by Lutz. Yeah, so we are done. So here is the letter from Kuhnel. So he told that he will be very happy if some of the conjectures is solved during his lifetime, and right. So and he also suggests that it will be some of these problems will be a good problem for the juniors who will do their PhD. And that's all. And thank you. So yeah, also Kuhnel suggested that in your email that if someone have problems, since I am not expert of this one, I have not read all the articles. I have seen just few of them. So if you have some questions, then you can email him directly. And if you need these slides, you can contact me. I will share this slide with you. And also, I talk about two papers that conjecture was solved. And these papers are also in our archive. And I have also those two. So if you want, you can ask me. I will also share with you. OK, so thank you.
Okay, so let's start with the second talk of session. Professor Jonathan Spear from Singh will tell us about an algorithm to compute the crosscap number of a knot. Already the pictures look very beautiful.
Okay. So, can everybody hear me online? Is that good? Okay. All right. Welcome everybody to this last mathematics talk for today, I think. So I will talk about an algorithm to compute the crosscap number of a knot, which is something I work together with Bas Jaco, Chaim Rubenstein, and Stefan Tillmann for a while. Maybe I should remove the mask for this talk. And but before I start with the talk, let me just explain to you what happened now. Okay. All right. Oh, okay. All right. Okay. So how I got here, right? So I'm a student of Wolfgang Kühnel. We just heard a talk from Wolfgang Kühnel. This is a picture here from my PhD defense in 2011. We see Wolfgang Kühnel here. That's me and some other people. This is Felix Effenberger, who was mentioned in the last talk as well. So from Stuttgart, I went to Brisbane, University of Queensland, and in late 2013, my contract was sort of about to expire, and we were looking for ways to sort of keep me employed. And then at some point, Ben said, well, there's really no funding opportunity unless you know someone in India. And then I said, well, hang on. I mean, I did a lot of work that is sort of connected to people here in this room, right? Basak and Basudeb Datta. And then I said, well, maybe we should give this a try. So, and because there was this Australia-India Strategic Research Fund program, and we were able to secure like a 3-year project called Building Triangulations for Fast Topological Computing. So this was under computer science, so we had to exchange combinatorics by computations, which is valid, I think, and which is also why I took the liberty to talk a little bit about computations when I really mean combinatorics. And as a result, 2014, we had Nitin and Basudeb visit the University of Queensland. We here together with Ben Burton, who gave a talk earlier today on the world famous city cat, like on the river in Brisbane. And also we did other things as well. I mean, Basudeb came back 2 years later. So we went a little bit sightseeing here. We see Nitin and Basudeb with Australian wildlife. You see Basudeb with more Australian wildlife. And here we are whale watching, and everybody's really excited because there were whales. But yeah, I don't know what Basudeb is doing on his phone. Yeah, and also, I mean, the other way around, Ben and I, we visited Bangalore 3 times. I spent, I think, 2 of my birthdays here, just because that was the best time to travel. Yeah, and we had, of course, food and everything. Okay, so that's how I ended up here. Last time I was here is 2016. Took a while to come back. We all know why. Yeah, but I'm happy that I'm here now. All right, okay, so for this talk, the talk is basically split up in 4 sections. First, of course, I will motivate a little bit why I'm looking at algorithms of 3-manifold topology, basically. Then I will talk a little bit about surfaces bounding a knot, a refresher on knot theory. That will not take very long. And the main part of this talk is devoted to normal surface theory, which is like a combinatorial tool to do actual topology in 3 manifolds. So quite, I want to say, as far as like combinatorial methods to explore topology of general 3 manifolds go, this is a pretty powerful theory, and we already heard a little bit about that in Ben's talk today. And in the end, if there's time, I will then talk about the result, how you can use normal surface theory to give an algorithm to compute the crosscap number of a knot, which is a classical knot invariant. Okay, so first, why do we care about 3 manifolds? Well, I have a basic assumption that everybody here likes manifolds, so likes 3 manifolds. Some people have strong, well, opinions about a particular dimension they find nicer than others. I don't really focus only on three manifolds, but that's an interesting dimension, let's say. And why do we study the crosscap number of a knot? Well, for two reasons. First of all, if you like knots, then the crosscap number of a knot is an interesting invariant because it's a little bit different than the genus of a knot, and it talks about orientable versus non-orientable surfaces in a class of three manifolds that are like knot complements. But in general, if you want to compute the crosscap number of a knot, you need to know a lot about surfaces in three manifolds. And actually, this program of coming up with this algorithm prompted a lot of research into actually looking at normal surface theory and what that can do. And that, in my opinion, can also sort of at least strengthen my understanding on how to study three manifolds through their codimension one submanifolds. Okay, so surfaces in three manifolds, as I already said, are an incredibly important tool to study three manifolds, which is not surprising. I mean, curves in surfaces tell you something about the surface, and so on. Just because codimension one means there's not much space left, right? So, for example, they can give you lower bounds for the number of tetrahedra you need to triangulate a three manifold. They can describe quantum invariants that are able to tell different three-dimensional spaces apart. And there's this framework, very beautiful framework called thin position that basically split up a manifold into simple handles and basically lets you sort of do topology in this way. So surfaces are really, really important. Some are more important than others, and we will come to that. Okay, so that's the motivation. We want to study, we want to understand surfaces in three manifolds. And in general, I want to say we want to understand codimension one submanifolds. So just a little bit of background so everybody knows what I'm talking about in terms of the crosscap number. So the setting for today, which is a more specific setting than in the paper we wrote about that, right? Where we don't just look at knot complements, but here let's just focus on knot complements because they're really nice and easy to understand. So we have a knot K, which is like an embedding of the circle in the three sphere. And we take this knot and a little neighborhood of it, so a solid torus out of the manifold, and then we get a three-dimensional manifold with a torus boundary, right? It's a special three manifold because it came from the three sphere. So we know many things cannot happen, right? We know where it comes from, but many things that work for knot complements also work for more general three manifolds. So there's surfaces embedded into this knot complement. So the closed surfaces are not that interesting just because we come from a three sphere and there's not much space to wrap around the surface, right? But the surfaces that bound the boundary, they are interesting. And if we look at this cartoon here, we have this knot in the three space. We drill out this solid torus. A solid torus always has this meridian disk, right? Yes. And we have this notion of a spanning surface, which is a surface where the boundary sort of runs along the knot. And this is, if you sort of shrink this neighborhood, it means basically that the boundary of the surface is the knot itself, right? And the only thing we want to we allow it to sort of spin around along the meridian disk, which it does here, but we're not allowed. It's not allowed to intersect the meridian disk more than once, right? And we of course it can intersect and then go back, but then we straighten it out. Okay, so this is a spanning surface, and sorry. Yes. So we will come to that in a second. Yes. So what these surfaces are called. Yes. So natural questions. Do spanning surfaces exist? Right. You could ask that. And what are their properties? And if you talk about a surface, what is the property? What's the genus? Right. So we have the genus of a knot, which is the smallest genus of an orientable spanning surface. And then we have the crosscap number, which is what the smallest non-orientable genus of a spanning non-orientable surface, right? Those are different things. If you look at a knot projection, there's like some neat tricks to actually find surfaces that bound this knot. You can have this there's this checkerboard coloring where you sort of color regions, in this case red and white, And if you think about this in dimension 3, you have these disks, and then you have these twists at the crossings. And what this gives you is, in this case, a non-orientable surface bounding the trefoil knot. This is a Möbius strip bounding the trefoil knot. So we know suddenly the crosscap number of the trefoil knot is at most 1. And I mean, it's actually, it doesn't bound a disk because that means it's a Diane knot, so it's actually 1 for the trefoil knot. And this is sort of the certificate. So this is a non-orientable surface. So we already answered the question, yes, spanning surfaces exist, at least non-orientable ones. If you want to have an orientable one, there's this nice Seifert algorithm where you kind of resolve your crossings and you have like layers. Like there's a top layer and a bottom layer, and you fill these layers with disks, and then you put in these bands with a twist. And it turns out that this is then an orientable surface, and you have your orientable surface. So now the problem is this out of the box cannot be used to compute the genus because there might be a smaller genus orientable surface, but it turns out that the genus of the knot can be computed for alternating diagrams, right? Reduced alternating diagrams. You can show that this Seifert algorithm, what I just described here, gives you the minimal genus surface, which is then called the Seifert surface. So usually you say the Seifert surface is the minimum genus orientable surface spanning a knot. So this algorithm of Seifert with these things, I just described this from the 1930s, the argument that this gives you the minimum for alternating reduced diagrams is from the late 50s. And only 2 years later, there was an algorithm by Schubert that used normal surface theory that actually answered this, gave an algorithm in the general, for general knots. And a little bit later, very interesting, there's this paper by Agel, Hass, and Thurston, where they say that the 3-manifold knot genus, so now we're talking about knots in 3 manifolds, is NP complete. So this is one of the first complexity results in 3-manifold topology. Yes, I believe that's it. Either fundamental solution or some tweak. Yeah. I think that's it. Yes. All right. Okay, so that's the genus. So the story is kind of finished here in the 60s. Now the crosscap number has a very different development, probably also because the genus is a bit more prominent, right? But so there's a formula for the crossing number of torus knots. So that is kind of special. So torus knots are knots that sort of are embedded on the surface of torus. They are like a pretty interesting class of knots. For various reasons. One of them is that you can read off the crossing number. There is a paper by Ben Burton and Amelie Özlin from 2012 where they give an algorithm to compute the crosscap number, but it breaks down in one case. So there's this one case where they cannot determine the crosscap number, and they say it's one of 2. Then there's an algorithm for alternating knots. And there's a nice inequality, which is quite fundamental, that says that the crossing number can never be larger than 2 times the genus of the knot plus 1, which is just, I mean, this is non-orientable genus, is twice in order characteristic the orientable genus. So if you have the Seifert surface, you can sort of undo like a boundary compression and sort of do a connect sum with a Möbius band, and then or a cross cap, and then you have a non-orientable surface bounding the knot, and then you're basically done. And this is this inequality, and this is exactly the case of equality is exactly where the algorithm from Ben and Melly sort of breaks down. Okay, so and we see here, and this is I think a very nice statement. There are knots where the cross cap number cannot be realized by an essential surface. Essential means it's incompressible and boundary incompressible. So sometimes you have to do this trick. And there's no non-orientable surface bounding the knot of minimum genus that cannot be sort of made easier than into an orientable surface. That's sort of a statement that I think is quite nice. Yes, you can compress it, it becomes orientable, and this is exactly what we have to fight with here. Okay, so How much time do I have? Half an hour. Okay, okay. All right. Okay, so now, how do we attack this? Normal surface theory, right? So before I can sort of tell you the result and how to prove this, I have to tell you about like the method and how do you actually improve. How do you construct algorithms like this and to solve these problems or others? Okay, so first of all, a triangulation. What do I mean by a triangulation of a manifold? We've seen this by Ben, right? This is again this one vertex triangulation business. I can sort of, if you like simplicial complexes, maybe I can sell you on the point that whenever you have something like this, the second derived subdivision is always a simplicial complex. So we are never far off, right? But in dimension 3, it turns out that many things are easier when you consider these one vertex triangulations. Okay, so what we do is we take a bunch of tetrahedra, we glue them along their faces, and we do a little check, right? That the vertex is surrounded by a two-sphere and so on, and then it's a manifold, and then we're happy, right? So when we say that T triangulates M if the carrier, the geometric carrier, is homeomorphic to M. And in dimension 3, there's no business with like piecewise linear structures and so on. Everything is fine. So we can identify two triangles of the same tetrahedron, right? And the unpaired triangles give you the boundary of it. So that's the same, right? Okay, so what can we do? So we can describe surfaces. A surface is somehow embedded in our 3 manifold. We say it's properly embedded, meaning that if it has boundary, the boundary must be on the boundary of the manifold. And we want to embed them in a certain way we call normal. So for this, look at a given tetrahedron. It has like these 7 normal disks. So you can chop off a vertex. You can do this with all 4 vertices, or you can separate 2 edges, right? The front and the back, the bottom left and the top right, or the top left and the bottom right, right? This gives you 7 disks. 3 of them are triangles, and 4 of them are triangles, 3 of them are quadrilaterals. And you immediately see that if you want to have a embedded surface that is sort of made out of these pieces, you cannot have 2 distinct quadrilateral types in one tetrahedron, because then they intersect and it's not embedded. I should have said before, a normal surface is now a properly embedded surface S in sort of the geometric carrier of T that happens to be made out of these pieces, right? So if we look at such a surface S and we intersect it with some tetrahedron of some manifold, then it will look like this picture on the bottom. Here you have like 3 parallel quadrilaterals, you have 2 parallel triangles in the bottom, and so on and so on and so on. All right. So if the surface intersects with every tetrahedron locally has this form, then this is a normal surface. Okay. So why is this useful? Well, because we have only 7 types of normal disks per tetrahedron, so we can have 7 integers, non-negative, of course, that describe us how many parallel copies we have from every piece, right? So here in this example, for example, we have 0, 1, 2, 2, 0, 0, 3, right? And this coordinate can then be translated into this picture, right? You can see how the coordinates are in one-to-one correspondence with the picture. And the last 3 coordinates that stand for the quads, 2 of them must be 0, right? Otherwise, it's not embedded. And now we want our surface to be properly embedded, which means that we must have something that's called the matching equations. Like these normal disks, they exit the tetrahedron. They have to go on to a similar normal piece in the other tetrahedron, right? So they must match up, and we have these nice linear equations, like the triangle from one tetrahedron and quad from one tetrahedron together. The number of parallel copies must be equal to like another triangle type and another quad type on the other side, right? It must match up. So we get these 7n, if n is the number of tetrahedron coordinates, and we have these 6n linear constraints. Why 6n? Because we have 2n triangles, and we have 3 types of arcs, so 6n, right? And this gives us a giant polyhedral cone, right? So, and normal surfaces are now translated into integer points in some Rn, R7n, positive orthant, subject to these matching equations. and subject to the quad constraints, which go, well, they make sure that 2 of the quadrilateral types are always 0. Sadly, this is a quadratic constraint, which sort of destroys our linearity of our setup. In this case, it's Q1, Q2 plus Q1, Q3 plus Q2, Q3 equals 0. That makes sure that always 2 of them are 0. And this polyhedral cone with the quadratic constraints is called the normal surface solution space. Right? There's another two separate things that are important later on. There's the weight of a normal surface, which is just the number of points, the number of times it intersects the one skeleton of the triangulation. Right? So we have our surface, it intersects the one skeleton in points, it's in general position. And if we sum them all up, we get the weight of the surface. We can also have the weight of edges individually. That's an important notion. And then there's the notion of the Haken sum, which is okay, which is if you take the normal coordinates, the coordinates of 2 normal surfaces, and you add them up in n to the 7n, and the sum satisfies these quad constraints. I mean, the matching equations are automatically met because we just add them up and they're linear. If this is again a valid vector for a normal surface, then the sum is called the Haken sum. And the Haken sum of 2 normal surfaces has one good quality, which is its Euler characteristic is additive, and has one bad quality, which is it destroys orientability. So 2 orientable surfaces added together can give you something non-orientable and the other way around. Any combination is possible because it is completely combinatorial. You throw them together and then they will sort of form a new surface. Basically, you have these intersections of 2 surfaces and they are resolved in some way and you don't have control over how they resolve, right? So here's an example of a Haken sum on tetrahedral basis. You just add them together, but then of course you don't know how they sort of match to the next tetrahedron, right? It could go this way, it could go the other way, right? But this is additive, and Euler characteristic is additive. Weight, of course, is additive, so that's good. Right? Orientability, yes. Well, if you have 2 orientable surfaces in an orientable manifold, it can well be a non-orientable surface in a Haken sum. I don't have an example, but I can't rule it out. Yeah. Well, it's yeah. Okay. So so now we come to the I want to say the most powerful bit in normal surface theory. So far, I just described to you like presenting surfaces as sort of in a cone. So the really good thing is now we have these integer points in cones with some extra constraints. Because we're in this cone can have a Hilbert basis, meaning like a collection of integer points in this cone, such that like every other integer point in this cone is like a linear combination of these fundamental or these elements in the Hilbert basis. So if we have a Hilbert basis of this normal surface solution space, then these points, the surfaces corresponding to these points, are called fundamental normal surfaces, right? And in other ways, you can say it's a normal surface that is not a non-trivial, cannot be a non-trivial Haken sum of other normal surfaces. So you break it down. You have funny things where like you take 2 surfaces and they give you in sum a third, and then you can take this and another one, and in sum it gives you one of the. Well, like it's not straightforward, as well. A Hilbert base is not straightforward, but you have this finite set, right? So you have the fundamental normal surfaces. They're kind of like a, yeah. I'm sort of throwing the quad constraints under the bus here, but point is they're sort of can be thought as a subset of a Hilbert base of the cone, and the take-home message here is there's finitely many of them, and you can actually give a bound. There's some constant such that there's never more than c to the n squared fundamental solutions where n is the number of tetrahedra. Okay, so I think this constant is pretty big, but again, as Ben said before, if you actually try to enumerate these fundamental normal surfaces, that is practicable up to 30 tetrahedra. And 30 tetrahedra give you many, many unknot complements, basically. All right. Again, you can use Regina to enumerate fundamental normal surfaces. All right. So what's the problem with normal surface theory? So far, I told you that there is kind of a finite description of all surfaces in a manifold that can be presented as normal surfaces. So the first problem here is that not every surface in T can be written as a normal surface, right? Just think of like a little sphere that is bounding a 3-ball inside a well, that's maybe a bad example, but think of a Heegert surface, right? So you have a Heegert surface that splits the manifold into 2 handle bodies. This turns out to be not always present as a normal surface. Sometimes that's not enough, right? You have to add like some octagons, and that's a different thing. So not every surface in T is a normal surface. That includes some important, topologically important surfaces. And not every normal surface is a fundamental, of course, right? It doesn't help that we have a finite description of an infinite space. We have like an Haken sum of unbounded length. How can we sort of find this surface if we have to add like an unbounded number of fundamental solutions? Yeah, no. By normal, like normal disks. So every normal surface, right? Not every. So okay. So here I say topological surface in the manifold. Yeah, just an embedded surface. No, no, not at all. But it has a significance for the normal surface. Yeah, and the thing is that we don't get to pick T, right? We don't get to pick T. And then not every normal surface is fundamental. So what do we do about these 2 problems? So the first problem can be solved by something that's called normalization. So we start with a topologically embedded surface. We push it off the vertices. We make sure it's sort of transversal to the edges. And then you keep going, right? I'll come to that in a second. And the second issue is more severe. So if you want to have an algorithm that finds a certain surface and then sort of in finite time tells you, yes, the surface exists, so we have a certain outcome of our algorithm, or no, the surface does not exist, so we have a different outcome. You cannot afford to go through like arbitrary length Haken sums. So this you can basically, there's a workaround by taking your initial triangulation and making it good in a certain sense. And the key word here is zero efficient, which is a finite procedure that it takes exponential time, worst case, but it's usually pretty fast, that eliminates all fundamental normal surfaces of positive Euler characteristic. So you don't have spheres, you don't have RP2s. And that is hugely important because Euler characteristic is additive under Haken sum. So then suddenly you still have the annoying Kleinbottles and tori, but they don't increase the Euler characteristic anymore. And then you're sort of in business almost. Okay, so punchline here is Haken sums can be controlled if we pick the right triangulation. And the punchline for A would be incompressible surfaces can be normalized. So maybe we can go through that. What happens during normalization? If you intersect your surface with an arbitrary triangle of our triangulation, it could look like very wiggly. So we just use isotopies to make it into these straight arcs. That's strictly speaking not even necessary. But we can also intersect the weight. We can decrease the weight of the normal surface by sort of pushing these return arcs of the one skeleton. We can have these little connected components, right, that then bound a disk. So we do like a compression of the surface, right? This changes the topology, but it only performs compression. So it means the surface was not incompressible to begin with. So it was a little bit too complicated anyway. But if you think about Heegert surfaces are compressible. So this could happen with a Heegert surface. And this is why Heegert surfaces not always occur as normal surface. And then you have like more complicated things as boundary compressions, right? Where here's the front is the boundary. So you can sort of do a boundary compression and you can delete components. So this is all that can happen during normalization. So you start with a topologically embedded surface, you bring it in general position, transversal to the one skeleton. You do these 4 operations, and then it's a normal surface. So a good thing is if you start with a compressible boundary, incompressible boundary incompressible surface, these 2 things cannot happen. This cannot happen, so you're left with an isotopy. So if you start with an incompressible boundary incompressible surface, normalization will not change the topology. So that's good, right? But I mean, maybe you remember what I said before, not every cross-cap number is realized by a surface that's boundary incompressible. Okay, so corollary normal surface theory is great for finding incompressible and boundary incompressible surfaces. This is exactly what happens in the algorithm by Haken for unknot recognition. This is what happens for knot genus and for Hakenness testing. This is even Hakenness means 3-manifold is Haken if it contains a incompressible surface. Basically, that's a result by Jaco Ortel. That's actually even better because it certifies that a vertex solution, which is like a smaller set than the fundamental solutions, is sufficient here. Non-examples Hilbert surfaces. All right, zero efficiency here. I will maybe very briefly just mention zero efficiency is a triangulation of a not complex. So this is like a tailored definition for this talk, right? Triangulation of a not complex is called zero efficient if it does not contain a normal surface with positive Euler characteristic. Right? And other than the vertex linking, sorry, yes, very good. Other than the vertex linking sphere, and vertex linking spheres do not really play a big role in Haken sum because they can be made disjoint from everything else. But it's a very good comment, yes. So okay, so we have a there's a result by Jaco and Sedgwick that says that if we have a bounded surface, right, a surface with boundary, and the boundary is a 2-triangle torus, then there's a very neat argument that says you cannot have a Haken sum on the boundary. So all the boundary components you see in all the Haken sums must all be parallel. This is a very nice, in the end, if you set it right, if you set up the proof, it's really, it comes down to like the orientability thing. It's a very neat argument, but because you have this 2-triangle torus, it must be a 2-triangle torus where isotopy is the same as normal isotopy, which is sort of just means that normal surfaces are basically everything you can see. You can only in a Haken sum with a bounded surface that only has one connected boundary component, you can only have one bounded Haken summand, and all the others must be closed. And that's key for us. All right. So how can we sort of approach this now? So keep in mind, we want to find a fundamental solution, a fundamental normal surface that certifies that realizes our cross-cap number. So we want to find a certificate that we can find the genus minimizing non-orientable surface bounding a knot in the set of fundamental solutions. If that's the case, we can just simply enumerate them all and then just look for the normal surface that has this desired property. Okay, so we have a zero efficient triangulation of our knot complement. So we start with a triangulation, we make it zero efficient. There's a very nice algorithm, I guess like Ben Burton refined it, that crushes these positive Euler characteristic normal surfaces and changes the triangulation until they don't exist anymore. And let's say we have a normal surface that spans the knot and that has maximal Euler characteristic, right? We don't know this, we just assume S is this surface, right? So we know the surface because its maximal Euler characteristic must be incompressible and boundary incompressible. Otherwise, you could sort of make it boundary incompressible, normalize it, and then it's not maximal, right, of Euler characteristics. So we know it's a normal surface. We can write it as a sum of fundamental surfaces, right? Fi are fundamental normal surfaces. Because of zero efficiency, we know everything is non-positive, and the Haken sum is additive, right? So this is a sum with no negative, well, no positive summons. So, and J. Cedric tells us only one Fi, and just say, let's say it's F naught, right? F naught has boundary and the others are closed. So what this really means is that the boundary surface kind of must have the maximum Euler characteristic, and all the other summons must have Euler characteristic 0. Otherwise, you would just start with S0. It has a higher Euler characteristic, right? So what we know is we start with S. That's our spanning surface of maximum Euler characteristic. We know it's one fundamental solution plus a bunch of tori. Could be Klein bottles, except it can't because we are not in a knot complement, and there cannot be a Klein bottle in knot complement because there's no embedded Klein bottle in the 3 sphere. Right? This is where we use the knot complements. So this is where we have to sort of work harder if we want a more general result. Okay, so how do we now prove that describe a algorithm for the crosscap number of a knot? So again, K is the knot in S3, M is the complement, T is the zero efficient triangulation. Now, one technical thing, we have these annoying boundary compressions. Turns out there is a cheap trick. We can turn the zero efficient triangulation into a triangulation where the meridian runs along an edge in the boundary. And with this, we can make sure that we cannot have a boundary compression as part of a normalization when we have an incompressible but possibly boundary compressible fundamental normal surface or normal surface. Anyway, that's a technical thing. That's anyway. Okay, so the theorem here, I think the plus. Yeah, I gave this talk at some point before. The plus can now be. It's on the archive, right? Okay, so. I guess the plus is still accurate because it's not published yet. Okay, so if we have the zero efficient triangulation of the complement of the knot with this extra boundary condition, then the crosscap number is the minimum of 2 numbers. The first is 1 minus the Euler characteristic for a non-orientable spanning fundamental normal surface. And the other one is 2 minus the Euler characteristic of an orientable spanning fundamental normal surface. So for one thing first, if we kill this fundamental here, this is a theorem about nothing, right? The only thing that's non-trivial is here the fundamental, right? Because of the setup, we always find these as normal surfaces. And if you look at the 1 minus Euler characteristic and 2 minus Euler characteristic, the case B is exactly that you find the cipher surface to be of very low genus. And then you do this undo this boundary compression, and you get this 2 minus the Euler characteristic. And that then realizes the crosscap number, maybe. Okay, so I have maybe a couple of minutes. I can maybe continue to say something of the proof. Oh, okay, so I explained the proof to you, except one thing, and that's the orientability issue. Right? We have this maximum Euler characteristic surface. We can rewrite it as a fundamental bounded surface with some tori. The problem is this fundamental surface may be orientable or non-orientable. We don't know. Okay, so we have, let's say we have spanning surfaces of maximal Euler characteristic. There's 2 of them, the non-orientable and the orientable one. And let's say Sn is the non-orientable spanning surface of maximum Euler characteristic, and let's say So is the orientable one. So we know from the setup that crosscap number is now the minimum of 1 minus chi of Sn or 2 minus chi of So. This is again Clark's inequality, which is then, which means that the crosscap number is at most the minimum of A and B from before, right? Because the normal surfaces, these surfaces are normal, but they might not be fundamental, right? So this is maybe higher. Okay. You always have to think like, Euler characteristic is negative, genus is positive, right? Yeah. Okay. So we have this incompressible non-orientable surface plus this special edge condition, which prevents us from doing a boundary compression during normalization. So we know this is a normal surface, and SO is incompressible and boundary incompressible. So this is also can also be normalized, right? So both Sn and So, we started out at topological surfaces. Those are normal surfaces. So the easy cases is where the Euler characteristic of these two things are distinct, right? If they're distinct, if the non-orientable one is smaller, then of course B is the Euler is the real is the answer for the crosscap number, which might be equal to A, but it's B. And if the non-orientable one has lower genus, right, higher Euler characteristic, then of course it's A. So J-concentric just gives us fundamental normal surface of the same Euler characteristic. It doesn't tell us something about orientable and non-orientable. So the tricky case is if these normal surfaces, again, have this, we assume they have the same Euler characteristic, right? And this corresponds to the only case where sort of Ben Burton and Meili Özlem sort of gave up, right? Like and left that. So, and this is where the real proof starts, where you then have to use facts of not complements that every torus is separating, and you study. This is here. You study these, like this is a torus. This is the rest of the surface. You study these Haken sums. And you have to be very carefully in taking like an arbitrary resolution of the surface as a Haken sum, and then you find these connected components you don't want, right? Because that just means there's a simpler solution, and you basically find out that sort of in this particular case, and this is really like a couple of pages analysis, you can show that the non-orientability is sort of preserved. If you start with something non-orientable, you will find the fundamental solution to be non-orientable. So there's a very nice part of the proof where you just have to count. You just have to sort of count intersections, and then if you look at this Haken sum, you can find this non-orientable sort of this orientation reversing loop. You can sort of show that it has to pass like everything at most once. And then there's like a parity argument that then lets you say that you can sort of split off most of the stuff and you can work with a much smaller set. So it works out quite nice in the end. One thing that I would also like to mention, we can implement this algorithm. And due to a lucky mistake where I ran this algorithm with a too optimistic setting that was way more efficient than another one. And Stefan Tillmann found out about this, and then we discovered, oh, this is not invalid. So Stefan just said, oh, I have an idea, and he just proved it in a more general setting, so that we now also have like a more efficient algorithm. Anyway, that's like a side story, but at the end of the day, we are also able to find I think 160, 170 new crosscap numbers of knots that where the crosscap number previously was unknown. I mean, you see some of them here. If you want to see the whole thing, you can go to knot info. It's like this knot database, but I think they said they will only put them in once it's published. I think, yeah, you have to check. Maybe it's also there with like an asterisk. Okay, yes, so this is the punchline here. This torus in Haken sum with the rest equals S if this is non-orientable. And you can basically, if you assume that R is orientable, then you can bring this non-orientability to a contradiction. Okay, so I want to stop with this picture here, which is like key of the ingredient of this, and it didn't find its way into the talk, and I was sad. So what you see here is the fairy tessellation of the hyperbolic plane, and this is sort of the organizing principle that lets you deal with boundary slopes on your torus, and how the Euler characteristic of a surface bounding the boundary with the slope changes as you do these layerings here. So this is like I spent a lot of time making this, so I wanted to make sure it's included. Anyway, okay, that's all. Thanks. Mm-hmm. So you mean a double? You mean like with this push in with the? Yes. I believe this is yes. And this thing, this surface with this extra crosscap might as well occur as a normal surface, but we don't have a guarantee. So it might even be there, but we don't have a guarantee. Yes. So the thing is that it's very difficult to find these examples where this B is actually larger, and then it's just a question of finding the right triangulation. So you surely find a triangulation where it's not there, but there might be a triangulation where it's there, and that's sort of triangulation dependent. Yeah. The smallest knot where this occurs is 7 crossings, I think. Yeah, but that has been described before. Like, yeah. Mm-hmm. Oh, okay. Yes, exactly. At some point, we tried to use that. So when we were thinking about when we were thinking about this picture here, we tried to just leave it as it is and just treat it as an immersed surface somehow. Only resolve like some of these. We then sort of shied away from proving anything like that, and we couldn't also find something. Yeah. It might be true. Yeah. Oh. Yes, so with the minimal surfaces, this is a very that's sort of the idea behind the three. Yes, stable minimal. Yeah, you have these unstable ones, and those are the almost normal surfaces. Those are the ones that basically are used by Rubinstein for the 3-sphere recognition, and those almost normal surfaces, these unstable ones, are also guaranteed to the set of these surfaces are guaranteed to contain Hegel surfaces as well. Yeah.
That genus was a triangulation.
A positive Euler characteristic.
Positive Euler.
Yeah. Yes.
But
yeah. So yeah, so I mean, when I say this, I'm also using the fact that I have a not complement in the 3-sphere. It's right that sometimes. Well, there is a more general statement, but it's more complicated. Like so, and there the statement is not about crosscap numbers, of course. It's about slope norm. Slope norm being what's the highest Euler characteristic surface bounding. Yeah, and it's exactly these kind of things like embedded Klein bottles, embedded RP2s. They are a big thing. Yeah. No. This the crosscap number is for not complements. And we have like the statement is different for. So for. Yeah. Yes. Yeah. Because otherwise you have this. RP3 is but you have this RP2 in RP3. Yes, and this is a real embedded RP2s are an obstruction that doesn't work well with normal surface theory. I mean, there's also this algorithm to produce a one-vertex triangulation. Doesn't work for manifolds that have embedded RP2s. So there's really, yeah, you have to have these kind of a number of you have to be careful with these. Yeah. So the hypothesis would exclude things like that. So I should look it up what exactly, but you have to exclude things like embedded Klein bottles and for the more general statement, you have to exclude these kind of things. Yeah. Before I say it,